I'll begin this lecture by reminding you of the proof of convergence of a sequence, of a definition of convergence of a sequence that we gave during the last lecture. So we say that a sequence Sn converges to L, that is the limit as n goes to infinity of Sn is equal to L if for every epsilon greater than 0 there exists a capital N, a real number, such that absolute value of Sn minus L is going to be less than epsilon if n is greater than capital N. And you might recall that this was a mathematical way of expressing the fact that you can make Sn arbitrarily close to L by taking n sufficiently large. And so today I'm going to try to use that definition to prove various facts about various sequences. And first, actually, let me prove the following theorem. The limit of a convergent sequence is unique. What this means, this is just a fancy way of saying that if a sequence converges, it can only converge to one number and not two. And the proof is going to use contradiction. So suppose that on the contrary, the sequence Sn converges to two different limits. And I'm going to label them L1 and L2. So that means that the limit as n goes to infinity of Sn is L1, and at the same time a limit as n goes to infinity of Sn is equal to L2. So somehow we have to prove that this is impossible. And let me draw a picture which should motivate. So let's put it here. Motivation. Let's say that we're in a number line, and I have two numbers, L1 and L2. Such that L1 is not the same as L2, because if they're the same, then the limit is unique. All right, so what does it mean that the sequence converges to a limit? That means that if I select some small neighborhood of L1, then eventually the terms of my sequence are going to belong to this neighborhood. Right, so I should be able to, it doesn't matter what the size of a neighborhood, for a sufficiently large n, Sn is going to belong to this neighborhood. Well, but the sequence also converges to L2 So that means that if I choose a neighborhood of the same size around L2, then Sn will have to belong to this neighborhood as well. And that obviously is impossible if epsilon is sufficiently small, right? Because the distance between L1 and L2 is a fixed number, so I can choose neighborhoods sufficiently small so that they're not intersecting, and yet Sn has to belong to both neighborhoods. And so that is where the contradiction should come from. And now let's see how we can write this mathematically. All right. So since L1 is not equal to L2, then L2 minus L1 absolute value, this is a finite number greater than 0. Okay? Well, if that is the case, then I'm going to select epsilon that is equal to L2 minus L1 over 4. And then, by definition of the limit, right, so epsilon now is some positive number. So I'm doing basically sort of a thing that you see in the picture. There is no magic about number 1/4, but if I make this distance less than 1/4 or 1/4 of a distance between L1 and L2, then in this way I will guarantee that this neighborhood and this neighborhood are going to be non-intersecting. So if I select epsilon like that, then by definition of the limit, there exists a number n1 in R such that Sn minus L1 is going to be less than epsilon. Right? So I chose epsilon, then by definition of a limit of Sn is equal to L1, I have this fact that I just written down. Similarly, again, by the definition of a limit, and now I'm going to consider the second limit as Sn, as n goes to infinity of Sn is equal to L2, there exists another number n2 in R such that I'm missing a piece above. Let me do it this way. Remember, this must be true only if n is greater than n1, such that Sn minus L2 is less than epsilon if n is greater than n2. Right, so I have two limits here. Each limit satisfies a definition. And so if I use a common epsilon in both definitions, I should be able to find true thresholds n1 and n2, such that if n is bigger than n1, then Sn is closer than epsilon to L1, And if n is bigger than n2, Sn is closer to L2 than epsilon. Okay, so now I'm going to set n to be the maximum of n1 and n2. If n is bigger than n, right, then I have two things. I have it number one, let me move this again. So if n is bigger than n, two things are going to happen at once. N is going to be greater than n1, right? Because if n is bigger than the maximum of n1 and n2. And second, n is going to be also bigger than n2. From here, Sn minus L1 is less than epsilon, and from here, Sn minus L2 is also less than epsilon. Okay, so Sn then is going to be less than epsilon on a distance less than epsilon from both L1 and L2. Alrighty. So then let's try to do this. If I compute the distance between L2 and L1, right, that's the absolute value of L2 minus L1, rather than measuring directly the distance from L2 to L1, I can go via Sn, and I can write this as L2 minus Sn plus Sn minus L1. And then by triangle inequality, this should be less or equal than L2 minus Sn plus Sn minus L1. So if I want to compute the distance from L2 to L1, by trying to go through Sn, then according to the triangle inequality, the distance that I'm going to cover would be either the same or greater. Well, because I have absolute values over here, then I freely can exchange the terms in the difference inside the absolute value. Absolute value of a positive or a negative number is going to be exactly the same, so I can rewrite this as absolute value of Sn minus L2 plus absolute value of Sn minus L1. And then if n is bigger than capital N, right, so if I'm in this situation, then that means that each of these numbers are going to be less than epsilon. So this is less than epsilon plus epsilon equal to 2 epsilon. And then remember how we selected epsilon. Epsilon was L2 minus L1 over 4. So I'm just going to substitute it back in. So this is equal to twice L2 minus L1 over 4, which is L2 minus L1 over 2. So if n is bigger than capital N. Right, not surprising, because if n is bigger than capital N, then Sn is closer than epsilon to L1. Sn is closer than epsilon to L2, which means that L1 minus L2 should not be bigger than 2 epsilon. And epsilon is L2 minus L1 over 4. But then what you see here, it follows from this. I can forget about the fact that I had n here, because what matters is that on the left I have quantity which is independent of n, right? It's just a difference of two limits. And on the right, I have a quantity which is independent of n. It's just another number which is difference of two limits. So my chain of inequalities basically tells me that L2 minus L1 must be less than L2 minus L1 over 2. And that certainly is not possible. So this is a contradiction. And so therefore our assumption that L2 and L1 were distinct, so L2 must be equal to L1, and the limit is unique. Okay. Let's do another example now. So this variant we just proved is basically an obvious fact which is about limits, which is clear, right? That a given sequence cannot converge to two different numbers, but now we use the definition of a limit to prove this conclusively or rigorously. All right. Let's do this. Let's take a limit as n goes to infinity 1 over n. If I just look at this limit, right, then it's clear. N gets bigger, 1 over n gets smaller. So this sequence must go to 0. And what I want to do, I want to prove this by using the definition. Now, what does it mean to prove this by using the definition? That basically means that I should be able to show that for every epsilon greater than 0, there exists a capital N such that the threshold capital N, such that if n is bigger than capital N, then Sn minus 0 is less than epsilon. So the proof is going to proceed in two steps. First, I'm going to try to determine what capital N should look like for a given epsilon, and then I'm going to verify the definition of a limit. All right, so choose any epsilon greater than 0. And what I want absolute value of 1 over n minus 0, I want that to be less than epsilon. Now, for which values of n would this be true? Well, let's see. So let me rewrite this on the next line. Absolute value of 1 over n minus 0. What is that? That's the same thing as absolute value of 1 over n. Absolute value is not needed for 1 over n because it's already positive, so this is just 1 over n, and I want 1 over n to be less than epsilon. How large should I take to make 1 over n less than epsilon? Oh, well, I can simply invert this inequality by properties of ordering to get that n should be bigger than 1 over epsilon. And so from here, I'm going to set capital N to be 1 over epsilon. All right? And so the definition of a limit will be satisfied if So now I'm going to check. Let n be bigger than capital N. If n is bigger than capital N, then capital N is 1 over epsilon, so then n is bigger than 1 over epsilon. If n is bigger than 1 over epsilon, again, dividing by n multiplying by epsilon, I'm going to get that 1 over n is less than epsilon. Then 1 over n I can write as absolute value of 1 over n minus 0 less than epsilon. And so what have I been able to do? I chose any epsilon greater than 0. For this any epsilon greater than 0, I found n, which is 1 over epsilon, such that if n is bigger than capital N, then my sequence minus 0 is less than epsilon. But that means that the definition of a limit is satisfied. So that is the definition of a limit. Checks out. And that means that I'm done. Okay, let's do example number 2. Now, let's do the same thing for the following problem. Limit as n goes to infinity. And then maybe let's take n divided by, maybe let's say 2n plus 3. Now, first of all, I want you to compute this limit, and second of all, I want to prove that your computation actually fits the definition of a limit. And now, to show what this limit is, right, we just use our previous knowledge of limits from calculus. So in this case, when n gets big, 3 becomes really relevant. So for very large n, essentially what you're seeing is n divided by 2 over n, and so that is nothing but just 1/2. So the limit is 1/2, and now I want to prove this again by using definition of a limit. Okay, let's see how we can do it. Follow the same strategy as in the previous example. So first, I'm going to choose any epsilon greater than 0. And what I want, I want the difference between Sn and the limit. I want that to be less than epsilon. So I want to be able to choose capital N such that if n is bigger than capital N, then this difference is less than epsilon. Sn minus the limit is less than epsilon. And so now I'm going to try to determine from this inequality in terms of n and epsilon, I want to figure out capital N in terms of epsilon. So essentially I need to solve this inequality for little n. Let's see how we can do this. Well, first of all, I need to put the left-hand side at the common denominator. So n over 2n plus 3 minus 1/2. That is 2n minus 2n plus 3 over 2 times 2n plus 3 absolute value. If we open the parentheses, this is 2n minus 2n minus 3 divided by 2 times 2n plus 3. And this simplifies to absolute value of minus 3, 2 times 2n plus 3. And if I take absolute value, the only thing that can be negative is minus 3 on the top. So its absolute value is plus 3, so this is going to be 3 over 2n plus 3. And so what I want is, I want this to be less than epsilon, and so now I can try to solve this inequality for n. First of all, we can divide both sides by, actually I can invert this inequality to get 2 times 2n plus 2 times 2n plus 3 divided by 3. This is bigger than 1 over epsilon. And now solve for n. So 2n plus 3, 2n plus 3 is bigger than 3 over 2 epsilon. And so n is bigger than 1/2 3 over 2 epsilon minus 3. Right, so no matter what epsilon is, how small it is, this will be a large positive number, so all of this is a large positive number in terms of epsilon, so I can make that equal to n. And so now, the second part, just like before, we're going to check if this n works. So check. Let n be bigger than capital N. And then I'm just going to follow, in fact, I'm not going to follow, well, actually, let me do it once. So if n is bigger than capital N is 1/2 3 over 2 epsilon minus 3, right? That's how we defined capital N. So if n is bigger than this number, then if little n is bigger than this number, then again I can manipulate this expression to become like this, and manipulate it to become like that, and then this will imply that this is true, and you just follow the same chain of inequalities backwards, and you arrive at this. Right? Because my computations here basically are saying if n is, if this expression in terms of n is less than epsilon, that it's analogous to saying that n and epsilon are related through this inequality. And so therefore, if n is bigger than capital N, it follows that my original statement must be true. So the definition of a limit is satisfied. Let's try another example. Let's say I want to take a limit as n goes to infinity of, let's say, n squared minus 3 over n to the fourth plus 2. Now, once again, from the previous life, you know that 3 and 2 here do not really matter when n becomes big. So this limit should be the same as the limit of n squared over n to the fourth, same as the limit of 1 over n squared, which means that the limit must be equal to 0 because the bottom grows like a fourth power of n and the top as a second power of n. So bottom always wins. So again, I need to prove this. By using the definition of limit. And again, very same strategy. Number 1, choose any epsilon greater than 0. And what we want absolute value of n squared minus 3 over n to the fourth plus 2 minus 0. We want that to be less than epsilon. Okay, so let's do the manipulations again. This stuff that I see on the left is such that I can drop 0, right, because 0 means nothing here. And then when n is bigger than 2, then the quantity inside the absolute value is always going to be positive, right? Because once n is 2, you have 4 minus 3. And because I'm taking the limit when n goes to infinity, I don't really care about what n does when n is small, what my expression does when n is small. All right, so I can drop the absolute value. So this should be, I'm going to write here, n is greater or equal to 2. Once again, if I'm taking a limit, I can start my sequence from anywhere, in particular at n equal to 2. So this would be the same as n squared minus 3 n to the fourth plus 2. And this must be less than epsilon. And you see that this actually is, if I look at this inequality, it's pretty nasty because not only I have an inequality, but it also involves fourth and second power of n for which I would like to solve. And so I can predict that the outcome is not going to look very pretty. So instead, we're going to try to take a shortcut, and that shortcut is enabled by the following property. Let me go back to the definition of a limit. So the limit exists if for any epsilon there exists an n, such that this difference is less than epsilon if n is bigger than capital N. The thing here is that there probably is smallest such capital N, the real threshold, such that if I pass through the threshold, then the quantity in a circle that is circled is going to be less than epsilon. But if I find capital N, which is maybe not efficient, but larger than this threshold, if n is bigger than this larger value, it's still bigger than the threshold, so this inequality still holds. The point being is I don't need to find an optimal capital N, but I find any capital N which is larger than an optimal, and demonstrate if n is bigger than capital N, then the inequality holds, and we're happy. So, with this in mind, capital N that I'm trying to find does not have to be the least possible capital N. So rather than saying that this fraction is going to be less than epsilon, first I'm going to try to manipulate it in such a way so that the fraction, I'm going to try to simplify it in such a way so that the fraction can only get bigger. If then I have a bigger fraction and it's less than epsilon, then this fraction will be less than epsilon. And here it actually is quite easy to do. So the first thing that I notice is that if I throw away minus 3 on the top, then I'm making denominator larger because I'm not subtracting 3 from it. So if I throw it away, the outcome is going to be strictly bigger. N squared over n to the 4th plus 2 is strictly bigger than my original expression. And then if I take plus 2, which sits in the denominator, and throw it away, then I'm going to make denominator smaller, and if I'm making denominator smaller, I'm going to make the ratio bigger. So this is less than n squared over n to the 4th. And then I can cancel n squared to get 1 over n squared. Certainly 1 over n squared is much simpler than the original expression. So if now I make 1 over n squared less than epsilon, then I'm making my original absolute value less than epsilon, right? Because all inequalities are less or equal here in this chain. All right, so then if 1 over n squared is less than epsilon, that's the same thing as saying n squared is bigger than 1 over epsilon, and that's the same thing as saying, once I have taken the square root, because everything is positive here, this is equivalent to n being bigger than 1 over square root of epsilon. And I'm going to set capital N to be that 1 over square root of epsilon. So then part number 2, if little n is bigger than capital N, then what will happen? Then I can follow this chain of inequalities backwards, right? If n is bigger than 1 over square root of epsilon, then n squared is bigger than 1 over epsilon, then all of this is true, and therefore that is true. So given an epsilon greater than 0, I can choose capital N like this, and then if I make n bigger than this capital N, then the difference between the limit and the terms of my sequence is less than epsilon. And so that means that the definition of limit holds in this case. And so that means that we actually proved that the limit in this situation is equal to 0. Okay, in the next lecture we're going to do more of these examples.